This is the Global Climate Change lecture, sharing it from your Content tab, which is where the full PowerPoint is listed. The vast majority of the climate change information can be found in your textbook, ebook through readings. But I wanted to make sure that you understand some of the key points. In the PowerPoint, there are a lot of slides, a lot of text slides that give you a lot of information. But I wanted to take about a half an hour or so to go through some of the key points to make sure that everybody understands climate change and, of course, the connections to the oceans and the marine system as they pertain to climate change. Now, first and foremost, you want to make sure that you understand that the concepts of the ocean system and the marine system are integrally linked to atmospheric circulation, right? In other words, what happens in the air, if the air is warming, it has a direct link to the sea surface temperature. So if the air is warming, the ocean is warming. The ocean absorbs and is heated by the surface layer of our atmosphere, but it also absorbs the gas or gases that are prevalent, namely carbon dioxide. Now that can have a whole bunch of issues. Right now we're just focusing specifically on what carbon dioxide is and does in the atmosphere and its links to impacts on ocean systems. Unfortunately, 15 of the last 17 years are the hottest globally on record. And unfortunately, the hotness trend is getting hotter. So it's not like they're all the same degree of hot, right? You can see an upward trend that hot is hot, but hot is actually even getting hotter. Now, before we get started with the main portion of the presentation, I want to make sure that you understand some basic concepts. I have already gone over these or will be going over these in class, depending on what section you're in. But I want to make sure you understand the main differences between the greenhouse effect, global warming, and global climate change. The greenhouse effect is what you're looking at here. Essentially, the sun is what is warming our Earth. In this case, it's what's warming this greenhouse. Now, a greenhouse should technically be called a glass house, but what it is it's a house that allows light penetration and heat in, but that from the inside blocks that heat from escaping out. It's essentially painted or covered by a very specific lining or film, again, or paint, that acts to stop the sun's heat and radiation from escaping. How this applies to the Earth is that you can think of the roof in this picture as the atmosphere of the Earth, and the painting or the panes of glass that are shaded gray as the gas that is in the atmosphere. So if we have gases in our atmosphere, namely carbon dioxide, but there are lots of others, we call those gases greenhouse gases because what they do is they block the ability for the incoming energy, which creates heat, to be lost. So the heat stays closer to the surface of the Earth, closer to the land, closer to the ocean surface, thus warming us unnaturally. That heat stays in, right? Even in the middle of winter, inside the greenhouse is warmer than the outside. Inside our Earth's atmosphere, as it is trapped by the gas, is warmer than it's supposed to be because the gases are unnaturally building, which is increasing our greenhouse effect, keeping that heat closer to the Earth's surface and therefore warming us. Now, this then leads to global warming. Global warming is simply a misnomer, but a correct term, but a misnomer in the sense that it used to be the title for this larger topic and no longer is, because we're not uniformly and only warming, right? The Earth still has seasons. The Earth still has cyclical change. It still has 4 seasons or 2 seasons, depending on where you are. But by and large, based on, of course, the figure that you just saw before, globally, on average, regardless if it gets warm and cold on a seasonal basis, we are warming. So we used to call it global warming. But people didn't like that term, right? Scientists didn't even like that term because it implies that all we're doing is warming. The trend of global warming is essentially saying that the climate on our planet, while getting warmer, is also experiencing incorrect, inaccurate, and consequential change. So we renamed it global climate change, which includes the warming of the Earth on a trajectory. That warming is happening because of the greenhouse effect and, of course, other instances. The fight about whether global climate change is real or not is typically not about is it or is it not happening. We're looking at the data that's telling us it is. But the fight then becomes, how is it happening, right? What is causing this increase in gases? Well, first and foremost, one of the arguments is that we always have had a natural change of climate, right? Back in prehistoric times, in medieval times, in between ice ages, we have had warming periods, and that is correct. However, as it tells you here, we are currently in an unprecedented change of climate. We have more extreme fires, droughts, storms, hurricanes, etc., as well as unprecedented heat all over the world for longer periods of time than we ever had in recorded history or even in ice age core data, etc. So we've never been able to find ever in the history of the Earth that we've done any testing this level of unprecedented, unnatural change to an Earth system. So we call that anthropogenic change. If humans are causing the change, anthropogenic means man-made. So we believe that global climate change is occurring because it is man-made, not based on natural causes, and the trajectory of the current warming is unlike anything we've ever had before. The trajectory is another argument that people sometimes come up with, that yeah, you know, we're kind of increasing, but we're not increasing for any big reason, and our increase can't be linked to anything. Well, by and large, you can pretty much take the increase in human population and overlay that on our dependence on fossil fuels, and thus an increase in that, our dependence on needing to cultivate the land, and thus an increase in that, a dependence on the production of ammonia, of course, from the production that ammonia is synthesized through from various industries, and then, of course, the reactive nitrogen creation. Again, all of these things, regardless if you understand what the ammonia synthesis is or cultivation, for example, all these lines are going upward, right? So the more of us that are on the planet, the more we are doing things, which is represented here, and the more stuff is produced. One of the key factors that we watch to determine the link between warming trends and production is right here under fossil fuels and under gases. As fossil fuels are burned, gases are created. As gases are created, temperature gets trapped and temperature increases. Those greenhouse gases that are mentioned before namely include carbon dioxide, but of course include a lot of others. Probably the second most popular is methane, but you don't ever want to forget about water vapor, ozone, extremely important. Another key figure that I'd like you to take a look at, that again should put any naysayers to rest, is if we look back in pre-industrial times, right here, you see again a little bit of a trend, an upward trend, but a pretty limited upward trend. And even if you went for 100 years, the trend, while up, again is pretty limited on an upward trend. And again, population was increasing, so of course gas production was increasing, carbon dioxide. But look what happens when you get to the 1950s. This trend, this line, is completely different from an angular perspective, right? From a trend perspective than this line here. This is pretty much a flat line, maybe a 5% incline. This is 90% incline or increase, right? So what it's telling us is that we've gone from less than 280 parts per million of carbon dioxide to over 400 parts per million of carbon dioxide in not a great period of time. What happened was the Industrial Revolution, which includes our dependence upon fossil fuels and oil, and of course the population boom, which led to our increased use and dependence of these things. We also, of course, because there's more of us, have cultivated the land more, decreasing the amount of trees and primary producers. So not only do we have less oxygen production, we have less stuff on the planet that can take carbon dioxide in. And so it gets sucked in by the surface layer of the ocean, causing ocean acidification, and ultimately creating that greenhouse effect that I mentioned before, ultimately leading in an increase in atmospheric temperature on the planet. So just a few key points before I show you some of the impacts and its relation to the ocean systems. You'll notice that probably the first 20 slides or so give you all the links and terms that you need to understand the climate system, the natural causes of climate change, how we've actually studied them, again, the greenhouse effect of what I showed you before, what our Earth's heat budget is, and it shows you all the data and figures that I had pointed out. Another key slide, which is a text slide that I want to point out before I move on, so that you understand what a very important agency is. It's called the IPCC, Intergovernmental Panel on Climate Change. Now, this is not just a group of scientists from the United States. It's a group of scientists globally that collectively have gathered for approximately the last 30 years to essentially determine how the temperature has been rising naturally, how the temperature has been rising unnaturally, and to predict where likely the global temperature will go if we don't make any changes, if we get worse with our production or population, etc. So they make all sorts of predictions. They release this giant, like 20-volume document or series of documents every couple of years or so, and everyone waits to see what this panel, they're the preeminent experts, everyone waits to see what this panel has concluded. Their basic global prediction is that we're going to have a change of approximately 1.4 to 5.8 degrees Celsius, which is pretty big when you look at Fahrenheit, which is what we're used to here in the United States. And that, again, is based on the fact that we're mimicking modern conditions and human emissions are not decreasing. So that's worst case scenario, right? We don't want that to happen. We don't just want to measure it and say, oh, we know where it's going to go. We want to measure it and be able to determine how we can make changes individually, globally, nationally, and internationally to then bring that number to a halt from increasing, and then figure out a way to get the carbon dioxide that's currently trapped there out so we can decrease that number. Now, what are the links to marine systems, marine habitats, oceanography? Well, there's a couple that should unfortunately play a pretty big role in things you've learned about in the course. We all know about phytoplankton and their link to primary production. Phytoplankton are primary producers. They are autotrophs. They live in the surface layer of the water. They need sun in order to produce oxygen. They also become the base of the food chain in ocean systems. Coastally, the water gets extremely warm. Coastally is also where you have a lot of runoff. Coastally, that runoff then can deplete the oxygen from the water, and or the water can become toxic or polluted from nitrogen runoff, from fertilizer, for example, pesticides, chemicals, etc. When that happens and the water either becomes lacking in oxygen or increased with contaminants, the phytoplankton will bloom. They will bloom in the color to which that species of plankton looks, and then you call it a red tide, brown tide, green tide, mahogany tide. You've heard all these different terms. Essentially, what that does is it lets you know that the water is toxic, right? Organisms that would filter feed on those phytoplankton still will, and then those mussels and bivalves and even fish become gummed up with this stuff essentially, and then they harbor and biomagnify or bioaccumulate these plankton. It also sucks the oxygen out of the water. Bait fish typically live close to shore because that is where smaller fish are going to be hunting for their food. Larger fish will then head upstream after their smaller prey who live in shallower waters. They will come in mass numbers. As those fish swim through the water into shallower waters, the water is lacking in oxygen for the reasons I just explained, and this many fish are going to be sucking a lot of oxygen naturally out of the water anyway, just in their respiratory process. So what happens is you get these massive fish kills. Now, these fish weren't killed because cyanide was dumped in the water. They literally have an anoxic or a hypoxic or a low oxygen level. That same issue can also cause distress in reptiles, birds, mammals. It doesn't just have to happen coastally. It can happen out in the middle of the open ocean based on oil spills and other issues. But you can have these die-offs in relation specifically to temperature. Now, how does the phytoplankton bloom that you just saw before and this fish kill, how do these things link to temperature? Well, if the surface layer of the ocean is warming and these fish are going into shallower waters, again, these plankton are in shallow coastal waters, that's the shallowest waters in our ocean system, that makes them the warmest water. Physiologically, chemically, warm water holds less oxygen. So you're now in a toxic environment with pollutants that is the warmest it can be, which therefore harbors the least amount of oxygen. You then have organisms hunting for food in those exact same places, and here you see the result. So when you have these massive heat waves, not only are the people struggling on land, not only are you having drought, not only are you increasing your chance for wildfire, you're also increasing trophic structure cascade collapses like phytoplankton blooms, like fish kills, all along coastal shorelines. Other issues as the warming trend occurs, and again, I just love to show you these figures that show that trend, right? There is an up and down. There's a natural up and down, but the trend from beginning to end is an upward trajectory, right? So if this trend continues and the Earth's surface temperature continues to go past, and we're heading toward about 2 degrees Celsius in the next 30 years or so, our trend for that warming not only will cause oxygen depletion in surface and shallow coastal waters of the ocean, but that increase is going to become catastrophic and exponential. And therefore, no matter where we look at it, no matter what year we're looking at, we're going to have a change not only in impacts in ocean systems, but changes globally on the planet. So the summers are going to come earlier, they're going to be hotter, the droughts will increase and last longer. In other places, water where it wasn't supposed to rain will rain longer, and you'll have increased flooding. You also can have flooding from storms and sea level rise. You're going to have mountains and glaciers that are melting, which again can lead to flooding and loss of habitats, contamination issues in the water, of course, and then loss as a whole of the ecosystems that are coastally and ecosystems that are based on ice, and therefore leading to extinction of the animals that live there. If we focus just specifically on ocean surface temperature, so if the Earth is increasing in temperature, then of course the surface layer of the ocean is as well. When you do sea surface temperature studies, notice that the reds are hotter. The hottest portions are in areas of the Earth that meet up with ocean gyre systems and sit in the area on the top or the North Pole in the Arctic. So in the area where the Arctic is, we have ice that forms every winter and is integral and necessary for, of course, the poster child of global climate change, which is the polar bear. So we're going to have issues in the Arctic for our poster child, which I'll talk about in a sec, but not only there are you going to have issues. Anywhere that that gyre or ocean system links can also have an impact. So locally on Long Island, Hurricane Sandy or Superstorm Sandy got renamed, right? A superstorm, bunch of storms hit at once. We know what that catastrophic impact can be. Coastal flooding, storm damage, billions of dollars in repair. This is no longer uncommon, right? We're going to have more high-level storms in places that we're not used to with infrastructure that can't handle it. And the warmer the storm, the higher the hurricane, right, in terms of its category, and the more damage. You may or may not remember or be familiar with how the ocean system generates, but our local, right here's Long Island, okay? Our local East Coast United States ocean current is called the Gulf Stream. It brings warm tropical waters from the south north, and it moves from south to north along our East Coast. As the water moves up, it's supposed to cool. When it cools, it will sink and join our deeper water in the ocean, giving us a warming and a cooling. Unfortunately, if the glaciers up above us are melting, you're going to have a freshwater input put into this system, and that change in temperature and salinity changes the density of the water. If we continue to have a density change of salty water and cold water, it will sink. But if we don't have a change, if the water is uniformly warm or uniformly fresh, those are not dense and it won't sink. And then unfortunately, you're going to have a catastrophic change to the North Atlantic circulation. So that circulation is connected to the Arctic that we had just discussed. The Arctic, unfortunately, the ice sheets in the Arctic are melting. We call it Arctic amplification. It means that the ice, which is seasonal, it grows and retreats naturally every year, is now not growing to as large of a mass as it used to, and it's melting earlier. And unfortunately, the organisms that then depend upon that ice are being harmed. Additionally, the ice is white, right? In the summer, what do? You wear a white t-shirt, you wear light colors because it doesn't absorb heat, right? It reflects heat. So if we have ice, it reflects that heat off and keeps our temperatures cool, allowing the ice to remain. When you expose ocean, which is darker in color, or you expose land, which happens and is a much bigger deal in the Antarctic, but anytime you expose a darker color, it's like wearing a dark color t-shirt in the summer. You absorb heat. So once you absorb heat, now you're even more warming those areas so that the ice cannot reform. Poster child, as I had mentioned, is the polar bear, right? Just like turtles are the poster child for not polluting with plastic bags and balloons, the polar bear hunts, lives, eats, breeds, and feeds on ice. If the ice is gone, the polar bear cannot do that. Another issue is that polar bears swim. They have to swim in order to be able to catch their food. But they don't swim forever, right? It's not a whale. It's a mammal that's a land-based mammal. It's a bear. They can swim comfortably about a mile, but then they need to rest for a very great period of time and feed. Unfortunately, you can see that there are smaller and smaller ice sheets that eventually won't support the weight of the bear, and the distance between ice sheets that can support the weight of the bear are becoming further and further apart. On average, polar bears are now swimming between 2 and 3 miles in order to get to a safe breeding, hunting, feeding ground. And unfortunately, they are beginning to drown. Another ocean connection or ocean example connected to climate change is called ocean acidification. Don't get worried with the crazy terms, right? But we're saying that if carbon dioxide in the atmosphere is absorbed by the phytoplankton in the sea surface, which is true, here's our increase of carbon dioxide in the ocean. Remember, carbon dioxide is an acid. So if we have increased carbon dioxide, our pH will decrease. Remember, a lower pH means acid. So as our pH decreases, we know that the ocean is acidifying. Now, what that means is there are a series of organisms in the ocean that are made of different types of shells. Some are silica, some are calcium carbonate. There's all different types of materials that organisms make their shells upon. Sometimes those shells are necessary to live pelagically or planktonically to stay in the surface layer to feed. Some, in phytoplankton examples, they must stay in the surface layer to be able to photosynthesize. Some, you need to build a shell in order to be hard enough to protect yourself. Some, you need a shell to be able to grow. But what happens is those shells become very thin, very feeble. They break easier. You also have an increased chance of infection and therefore not success. The issue with the phytoplankton that I had discussed before in ocean acidification links right back to the same coastal zone, right? So if we have increased phytoplankton in these specific areas and increased issues in coastal areas, these are also the same areas that we fish for our shellfish, mussels, clams, oysters, scallops. They are filter feeding, which is great because they're cleaning our water, but they're also filter feeding in these toxic phytoplankton. We then eat these organisms or portions or dozens of these organisms at clam bakes and such, and you get something called paralytic shellfish poisoning. So here's a connection of a coastal ocean issue that then goes right back to the dinner table, right? So it doesn't just have to be far off, right? Thinking about an organism whose shell becomes feeble. Now you have a shelled organism that lives in the water that is now becoming contaminated, which then becomes an issue for you. And of course, if you're a fisherman or in the restaurant business, that has a dramatic impact. Finally, I'd like to wrap it up with talking about sea level rise and coral bleaching. Corals are animals that live in calcium carbonate in coral reefs. Inside of the stomach, essentially, of a coral is the harboring of a photosynthetic phytoplankton. So they live symbiotically, essentially, with an animal and a phytoplankton in its belly. If the phytoplankton becomes sick, in the exact same way that we discussed with the surface layers of the water becoming toxic, right, when we were talking about the red tide, brown tide, right? So same concept. If these organisms in the gut cavities of these animals become toxic, the animals will expel them, right, essentially get rid of them. That's what provides the color to the reef. So now what you're seeing, this white, we call it coral bleaching. This white is representing rock. Rock without a living animal, without a living phytoplankton. That means they're not photosynthetic, which means the actual structure, the habitat, the ecosystem of the coral itself is lessening. This can also lead to death completely of a coral. 2 degrees Celsius increase in ocean temperatures will lead to the mass extinction of coral reefs. And finally, as I had mentioned that I was going to end with, sea level rise, because it's something that we all notice and can take heart of on Long Island. Our sea level is rising exponentially in the Northeast United States because of the issues I had mentioned before with the melting and issues in the Arctic. But if you're a low-lying island in the Pacific, think Micronesia, right? You're really at odds, and the entire livelihood of your nation is dependent upon the fact that the seas cannot rise. But sea level is rising. This island nation used to have a shoreline out here, meaning all of this space used to be habitable by humans and no longer can be. So that same general population, about 270,000 people who used to live on this size of an island, now either have to leave and become island refugees or live in a smaller portion. So sea level rise is real, not just locally, but globally as well. All right, so let's look at some potential possibilities, right? Let's think positively so we can end this lecture on a positive note. It's not too late to do the right thing, okay? Please make sure that you're doing your role, you're doing your job, you're doing whatever you can to decrease your personal creation of greenhouse gases. Decrease your energy use, change how you operate from a transportation perspective, change how you eat, change the companies that you support. But then ultimately science is going to have to step in. We've gone past the point of our ability to naturally correct ourselves, but we still have natural processes that we can utilize to help with our correction. The ocean is one of those. The ocean naturally sucks carbon dioxide in, right? The CO2 pump, the biological pump, in the same way that a plant outside sucks CO2 in. The phytoplankton pull it into the water. This then causes the ocean acidification in the surface layer. However, if we can sink that material to the bottom and deposit it on the bottom layer, that is one way to sequester or harbor carbon dioxide. There's only a certain level or amount that this can occur, and we also don't know what the implications will be if we were to sink too much of it unnaturally to the bottom of the ocean floor. In the same way, we've also tried to do this exact same type of experiment with iron. We've tried to, quote, fertilize the ocean to increase the productivity. In other words, to increase the amount of CO2 sucking organisms in the water that can then sink to the bottom of the ocean floor, ultimately removing carbon dioxide. We're trying to sequester or trap carbon dioxide in our ocean systems. We have been pretty much unsuccessful on a grand scale of this to date, but it's something, right? It's something for us to be working on and heading toward. It has some positives and some negatives as well. Ultimately, we need to look at all of our different options. We know that increasing primary producers, increasing autotrophs help, but ultimately that production of carbon dioxide would also have to decrease at the same time that we're taking that material out of either the ocean layer or the air layer. It's also really important that you vote and that you support politicians and agreements that support the Kyoto Protocol. We had a president recently that did not support the Kyoto Protocol, who had pulled us out essentially of the agreement. We were one of only 2 nations in the entire world to not be in the agreement. We are now back in. It is voluntary, so we were able to go out and in essentially, but it's a voluntary limit on limiting greenhouse gases. Maybe, for example, curbing emissions by requiring certain industries to change their emission standards, or curbing emissions by requiring car manufacturing to increase their capabilities, right, to produce cars that don't have as many emissions. That also allows for us to get incentives on tax breaks, etc., on our homes, on the cars that we choose to drive. And if we choose to buy the right kinds of products and run our homes correctly, we would be given an incentive to do so. So joining into these types of protocols, being in these international agreements, means we're all collectively working together. Because there's a famous saying that says, we literally only have one thing in common: the earth. And what happens in India and what happens in China impacts us in the United States. What happens in the United States impacts what happens in Africa and Micronesia and everywhere else in the world. We are not separate countries sharing an earth. We are one earth, collectively together, living here. And we do know for a fact that human activities are altering the global environment. Here is a list of a bunch of things that we are focusing on in an effort, again, to try to help with carbon emissions. So of course, we want to stop any more trees or primary producers from being removed. We want to stop the surface layer of the ocean from being polluted so the phytoplankton can do their job. We want our cars to be more efficient. We want us to use public transportation more so that we're driving less. We want to increase our dependency on biofuels and decrease our dependency on fossil fuels. We want our power plants to be more efficient. We want power plants to be able to store carbon dioxide, and industry as a whole to be able to either not produce or store carbon dioxide so that it's not released into the atmosphere. We want to look at different types of power: nuclear, hydropower, solar, right? Wind power. There are all sorts of different, more environmentally friendly choices. And we want to overall reduce our electricity use and our dependency. If we stopped greenhouse emissions today, we will still be warming by 0.9 to 1.8 degrees Fahrenheit soon. Remember, 2 degrees is the tipping point. We need to cut current emissions by about 80% to have a real impact. That means we collectively have to agree globally to decrease our emissions, not keep it at current standard and not produce more, literally decrease our number by 70 to 80%. If we don't, we are going to have a carbon dioxide level in the atmosphere in excess of 500 parts per million and a sea level rise of feet, right? This is in inches, so 12 inches in a foot, right? Feet by the turn of the century. Mainly with polar ice, which will of course result in no habitat for our polar bears, but ultimately in islands like Long Island, causing a massive sea level rise and a displacement of us, just like that island I had shown you before. So do your part. And that ends the climate change or global climate change PowerPoint.